Stop for a second. You perceive time as something constant, like a steady forward motion, second by second, day by day. But what if that's an illusion? What if time isn't a straight line, but something that can be bent, stretched, or even bypassed? What if, somewhere right now, someone already knows what will happen tomorrow, not because they're guessing, but because, for them, it's already yesterday? Physics says, time isn't the same for everyone. It slows down. It speeds up. It depends on speed and gravity. And if that's true, then the question isn't whether time travel is possible, but rather whether anyone has already done it. And if so, what would it look like? Maybe not at all like in the movies. Maybe without machines, without glowing, without special effects. Maybe it would look like a person who simply does the impossible. The year is 2003. The month is March. The location is the concrete and steel canyons of New York City, specifically the district known to the world simply as Wall Street. It is a time of high anxiety. The world is still reeling from the aftershocks of the dot-com bubble bursting. The geopolitical landscape is fracturing. The markets are volatile, a churning ocean of red and green numbers where fortunes are made and lost in the blink of an eye. In this chaotic ecosystem, there are predators, there are prey, and there are the lucky ones. But then, there is Andrew Carlson. Carlson does not fit the profile of a Wall Street wolf. He is 44 years old, nondescript. He does not have the pedigree of the Ivy League, the connections of the Hamptons country clubs, or the aggressive swagger of the trading floor veterans. He is a ghost in the machine. And yet, over a period of just 2 weeks, this unknown man performs a financial miracle that defies every statistical model in existence. He sits down at a computer terminal with an initial investment of $800, a modest sum, barely enough to pay rent in the city, and he begins to trade. He does not play it safe. He does not buy blue-chip stocks and wait for steady growth. He engages in 126 high-risk trades. He bets on stocks that are plummeting. He shorts companies that everyone else believes are solid. He buys into obscure firms moments before they announce a breakthrough. Every single move he makes is perfect, not just good, not just lucky, but mathematically perfect. He buys at the exact bottom of the dip and sells at the absolute peak of the spike. He never loses, not once. In the casino of the global economy, where the house always wins eventually, Andrew Carlson beats the house 126 times in a row. By the time the Securities and Exchange Commission notices the anomaly, the initial $800 has metamorphosed into a fortune of $350 million. Hello there. Tonight we are going to open a case file that sits on the borderline between criminal history and science fiction. We are going to look at the story of the impossible man, a figure who appeared out of nowhere, broke the laws of probability, and then vanished into thin air. We are going to use this story as a doorway to explore one of the most fascinating and perplexing concepts in physics, the nature of time. If you enjoy these deep, quiet investigations into the mysteries of our universe, please take a moment to like this video and subscribe to my channel. It helps me keep the archives open. To understand why the arrest of Andrew Carlson matters, we have to understand the nature of the stock market. The market is often described as a chaotic cyst, influenced by billions of variables, the weather in Brazil affecting coffee prices, a political speech in Europe affecting oil, a rumor on the internet sending tech stocks into freefall. It is a system of such staggering complexity that it is considered mathematically impossible to predict with 100% accuracy. Even the greatest investors, the legends of finance, get it wrong. They hedge their bets. They diversify. They accept losses as part of the game. But Carlson didn't hedge. He played the market with the precision of a man who had already read tomorrow's newspaper. When the SEC computers flagged his portfolio, the red light started flashing. A growth curve like that, from 3 figures to 9 figures in 14 days, is not just suspicious. It is indicative of a crime. The regulators assumed the obvious: insider trading. They believed Carlson must be the frontman for a massive, illegal conspiracy, getting tips from corrupt CEOs, leaking merger details before they went public. So they called the FBI. On a cold morning in March, federal agents arrested Andrew Carlson. They brought him into an interrogation room. It was standard procedure. They expected him to crack, to ask for a lawyer, to cut a deal, to give up the names of the corporate insiders who had been feeding him information. They sat him down under the harsh fluorescent lights, the hum of the ventilation system, the only sound in the room, and they asked the simple question, "How did you do it?" They were ready for a lie. They were ready for a confession. But they were not ready for what Carlson offered. He looked at the agents, calm and unruffled, and he said, "I am a time traveler." The agents likely laughed. It is the kind of thing a desperate con artist says when pleading insanity. But Carlson didn't stop there. He explained that he had traveled back in time from the year 2256. In his era, he said, the history of the stock market, the booms, the busts, the crashes, and the rallies was public knowledge, recorded in the archives like any other chapter of history. He had memorized the data for this specific period. He admitted that he had intended to lose a little here and there, to make his trading look natural. But he got greedy. The temptation of the perfect trade was too strong. He got caught in the rhythm of the win. The FBI, of course, did not believe him. They demanded evidence. "If you are from the future," they said, "prove it." And this is where the story takes a strange turn. Carlson didn't produce a futuristic device. He offered information. He offered to reveal the exact location of Osama bin Laden, who was, at that time, the most wanted man on earth. He offered to reveal the cure for AIDS. He offered knowledge that no human being in 2003 could possibly possess. The agents were skeptical, but they were investigators. They started digging into Andrew Carlson's background. In the modern world, you cannot exist without leaving a footprint, a birth certificate, a social security number, school records, tax returns, credit card history. You are a data point in the system. But when the FBI ran the name Andrew Carlson through their databases, they found nothing. No birth certificate, no driver's license, no tax records, no address history. Before December 2002, Andrew Carlson simply did not exist. It was as if he had materialized out of thin air on the streets of New York just a few months prior. His fingerprints matched no one in the criminal databases. His face matched no missing persons reports. He was a biological entity with zero history. This absence of evidence is often cited as the most chilling part of the story. It is possible to forge a passport, to create a false paper trail, but it is incredibly difficult to have no trail at all, to be 44 years old and have never bought a coffee with a card, never rented an apartment, never paid a bill. That feat of invisibility rivals the time travel claim itself. While the investigation continued, Carlson was held at Rikers Island, awaiting a bail hearing. The media caught wind of the story. The Wall Street wizard who turned pocket change into an empire. The time traveler angle was mostly suppressed, treated as a tabloid rumor. Then came April 3rd, 2003, the date of the hearing. But when the bailiff went to retrieve him, the cell was empty. Andrew Carlson was gone. He had not been released. He had not been transferred. He had simply vanished. Shortly after, An anonymous benefactor paid his bail using a bank account that couldn't be traced, but the man himself had dissolved into the ether, and he was never seen again. Was he a real-time traveler who returned to 2256? Was he a master con artist with connections powerful enough to erase his existence? Or was the entire story a modern myth, an urban legend born from the anxieties of a post-September 11th world that desperately wanted to believe in a future where we survive, where we cure diseases, where the stock market is just a history book? The story of Andrew Carlson was originally reported by the Weekly World News, a publication known for satire and fabrication. It is in all likelihood a fiction, but the reason it resonates, the reason we are still talking about it more than 20 years later, is because it touches on a deep, primal question that humanity has asked since we first understood the concept of tomorrow. Can we go back? Can we go forward? Is time a straight line, an arrow that flies only in one direction? Or is it a landscape that can be traversed? The idea of time travel is not new. It didn't start with Andrew Carlson, and it didn't start with Hollywood. For a long time, it wasn't even considered a subject for science. It belonged to the realm of gods and wizards. In ancient mythology, time was often cyclical, a wheel that turned and turned, repeating the same ages of gold, silver, and iron. Or it was a river, flowing from the source of creation to the ocean of the end times. But you couldn't swim upstream. It wasn't until 1895 that the concept was given a machine. Herbert George Wells, a British writer with a mind far ahead of his Victorian era, published The Time Machine. Before this book, if characters in stories traveled to the future, they usually fell asleep, like Rip Van Winkle, or were shown a vision by a ghost, like Scrooge. They were passive observers. Wells changed the vocabulary. He introduced the idea of a device, a machine made of brass and quartz and ivory, with levers and dials that allowed a human being to steer through the fourth dimension just as they might steer a car down a road. Wells treated time travel not as magic, but as engineering. He popularized the idea that time is just another dimension, like length, width, and height. If you can move forward and backward in space, why not in time? This idea captivated the world and sparked a genre. In Newton's world, Andrew Carlson is impossible. You cannot jump to 2256, because 2256 doesn't exist yet. The past is gone, burned to ash. The future is an unwritten mist. There is only the now. But then, in the early 20th century, a patent clerk in Switzerland changed the rules of the game. Albert Einstein looked at the universe and realized that Newton's clock was wrong. Time is not a rigid stage. It is a fabric. It is flexible. It can stretch. It can shrink. It can warp. Einstein proved that time is personal. My time is not your time. A second for me might be 1,000 years for you, depending on how fast we are moving and how close we are to a massive object. This was the birth of special relativity, and later, general relativity. And buried within the mathematics of these theories, physicists found something startling. They found loopholes. They found permissible geometries of space-time that looked suspiciously like paths to the past. Suddenly, time travel moved from the pages of H.G. Wells onto the chalkboards of theoretical physics. It wasn't easy. It required energy on a scale that could destroy stars. It required exotic matter that might not exist. It created paradoxes that threatened to unravel logic itself. But it wasn't impossible. The laws of physics, as we understand them, do not strictly forbid a man from 2256 standing in a room in 2003. So while Andrew Carlson might be a fictional character, the shadow he casts is real. He represents the ultimate fantasy, the ability to escape the prison of the present. to correct our mistakes, to know the outcome before we place the bet. But if time travel is possible, how does it work? Is it like Back to the Future, where you fade away if you change the past? Is it like Avengers Endgame, where changing the past creates a new timeline? Or is it like Interstellar, where the future influences the past in a closed loop? To understand this, we have to strip away the fiction and look at the raw mechanics of the universe. We have to look at what Einstein actually said. We have to understand the river of time. This brings us to the first scientifically proven method of time travel. It is not a theory, it is a fact. It has been tested. It has been measured. Humans have already done it. We are all time travelers, drifting forward at the steady pace of 1 second per second. But some of us have peeled away from the herd. They have traveled into the future, just a fraction of a second, but enough to prove that the door is unlocked. We are leaving the interrogation room of 2003. We are leaving the mystery of Andrew Carlson behind for a moment. We are going to look at the real-world evidence, to travel to the orbit of the Earth, to the domain of satellites and cosmonauts, to see how speed can sculpt time itself. And tonight we are going to look at the strange, elastic, fluid nature of the temporal world. We are going to see how a fast rocket is a time machine, and how a heavy planet is an anchor that drags the hands of the clock. The mystery of 2003 was a story about money, but the mystery of the universe is a story about time, and that story is far stranger and far more beautiful than any stock market trade. Albert Einstein wasn't working in a university lab. He was sitting at a desk, reviewing patent applications for electrical devices. But in his mind, he was riding a beam of light. He asked himself a simple, childlike question. If I could travel at the speed of light and held a mirror in front of my face, would I see my reflection? If light travels at a constant speed, and he was also traveling at that speed, the light from his face would never reach the mirror. It would be frozen. But if he couldn't see his reflection, that would violate the principle that the laws of physics should be the same for everyone, regardless of how fast they are moving. To solve this paradox, Einstein had to break the universe. He realized that for the speed of light to remain constant, which Maxwell's equations of electromagnetism insisted it must, something else had to give. Space had to give. Time had to give. He published his special theory of relativity, and with it, he shattered Newton's master clock. Einstein proposed that time is not a constant. It is relative. It can meander. It can be eddy. And the force that controls the speed of this flow is motion. This is the concept of kinematic time dilation. Simply put, the faster you move through space, the slower you move through time. Imagine you are standing on a train platform. A train whizzes past you at close to the speed of light. Inside the train, a passenger drops a ball. To the passenger, the ball falls straight down. But to you, standing on the platform, the ball moves diagonally. It travels down, but also forward with the train. The path of the ball is longer for you than for the passenger. Since the speed of light is the absolute limit of causality, if the ball travels a longer distance from your perspective, it must also take a longer time to do it. Therefore, you see the events on the train happening in slow motion. You see the passenger's watch ticking slower than yours. You see their heart beating slower. To you, they are living in a slowed down reality. But here is the mind-bending part. To the passenger on the train, everything is perfectly normal. Their watch ticks normally. Their heart beats normally. When they look out the window at you, standing on the platform, you are the one rushing past them in reverse. So from their perspective, your time is the one moving slowly. This symmetry is deeply confusing, but it breaks down the moment we introduce acceleration, when one person actually leaves and comes back. This is the famous twin paradox. One twin stays on Earth, the other boards a spaceship and flies to a distant star at 99% the speed of light, then turns around and flies back. For the traveling twin, the journey might feel like only a few years. They read books, eat meals, and sleep. Perhaps 5 years pass for them, but when they land back on Earth, they find that 50 years have passed for the twin who stayed behind. The traveler is still young. The Earth twin is old, or perhaps gone. The traveler has effectively jumped into the future. They have skipped over decades of history. This is not a trick of perception. It is a physical reality. Their biological clock, their atomic clock, the decay of every atom in their ship, everything slowed down relative to Earth. For decades, this was just mathematics on chalkboards. Critics called it absurd. But in 1971, two physicists, Joseph Haefel and Richard Keating, decided to put Einstein to the test. They didn't have a spaceship. They had commercial jetliners. They took 4 cesium atomic clocks, devices so precise they lose only 1 second every few million years, counting the vibrations of cesium atoms, the heartbeat of modern timekeeping. They synchronized them with a master clock at the U.S. Naval Observatory in Washington, D.C. Then they bought plane tickets. They flew around the world twice, first eastward in the direction of the Earth's rotation, then westward against it. This distinction was crucial because the speed of the plane adds to or subtracts from the speed of the Earth's rotation, changing the total velocity of the clocks relative to the center of the planet. When they landed and brought the clocks back to the laboratory, the question hung in the air. Had the clocks drifted, or had they stayed perfectly in sync with the one on the ground, as Newton would have predicted? They checked the data. The clocks that had flown east had lost time, about 59 nanoseconds. The clocks that had flown west had gained time, about 273 nanoseconds. The numbers matched Einstein's predictions almost perfectly. The difference was tiny. A nanosecond is 1/1000th of a second. But it was real. The clocks on the planes had experienced a different amount of time than the clock on the ground. Time travel was no longer fiction. It was an experimental fact. Since then, this has been confirmed thousands of times. But the most human example involves a cosmonaut named Gennady Padalka. Padalka is a Russian cosmonaut and a hero of the space program. He has spent more cumulative time in space than any other human being. A total of 879 days across 5 missions. For nearly 2.5 years of his life, he was orbiting the Earth aboard the Mir space station and the International Space Station. The ISS travels fast. It orbits the Earth at about 27,600 kilometers per hour, fast enough to circle the entire planet every 90 minutes. Because Padalka was moving at that speed for such a sustained period, the effects of time dilation accumulated. His personal clock ticked slower than the clocks on Earth. He aged slower. His cells divided slower. All of this relative to us down on the surface. When he finally returned to Earth for the last time in 2015, physicists calculated the difference. Gennady Padalka is currently about 0.02 seconds younger than he would have been had he stayed on Earth his entire life. He's effectively traveled 1.02 seconds into the future. It isn't much. You wouldn't notice it in a conversation. But in the strict language of physics, he is a time traveler. He has broken the symmetry of time. He has disconnected his timeline from the rest of humanity and reconnected it at a slightly different point, and this has immediate practical consequences for our daily lives. We rely on time dilation every time we use a phone to navigate. The Global Positioning System, GPS, consists of a constellation of satellites orbiting the Earth at about 14,000 kilometers per hour. Because they are moving fast, special relativity says their clocks should tick slower than clocks on the ground, by about 7 microseconds per day. However, there is a counter effect. The satellites are also far from Earth, about 20,000 kilometers up, where gravity is considerably weaker. According to general relativity, time moves faster where gravity is weak. This effect speeds the satellite clocks up by about 45 microseconds per day. So you have two competing forces, speed slowing time down and low gravity speeding it up. When you do the math, 45 minus 7, the net result is that satellite clocks tick faster by about 38 microseconds per day. 38 microseconds sounds like nothing, but light travels 300 meters in 1 microsecond. If engineers didn't account for this relativistic drift, GPS errors would accumulate at a rate of roughly 10 kilometers per day. Within days, your navigation app would tell you that you were in the middle of the ocean when you were actually in your driveway. The entire system would collapse. Every time you successfully find a coffee shop using GPS, you're validating Einstein's theory of time dilation. You're relying on the fact that time flows differently in space than it does on the ground. This realization, that time is a fluid, dynamic thing, changes how we view the universe. We tend to think of now as a universal concept. We assume that when I snap my fingers, that now is the same moment on Mars or on a planet in the Andromeda galaxy. But relativity destroys the idea of simultaneity. There is no universal now. If you and I are moving at different speeds, we cannot agree on the order of events. I might see event A happen before event B. You, moving rapidly past me, might see event B happen before event A, and we would both be correct. The sequence of reality depends on your trajectory through it. This leads to the concept of the block universe. Many physicists believe that past, present, and future are all equally real, that they exist together in a four-dimensional block of space-time. Think of a loaf of bread. You can slice it at different angles. Each slice represents a moment of now for a specific observer, depending on how fast you are moving. Your angle through the loaf, your slice will include different parts of the whole. In this view, the past hasn't vanished. It is just further down the loaf. The dinosaurs are still roaming the earth in their slice of space-time. Your birth is still happening. Your death is already there, waiting in the future. We are just conscious spotlights moving through the block, illuminating one slice at a time. Time travel, then, is simply changing the angle of your slice. It is finding a path through the block that loops back or jumps forward. So, if speed can slow down time, what happens if we go faster still? What happens if we approach the ultimate speed limit of the universe, the speed of light? As an object accelerates closer to light speed, time dilation becomes exponential. At 50% of the speed of light, time slows down by about 15%. At 90%, time slows to less than half. At 99.9%, 1 year for the traveler equals 22 years for the people back home. At 99.9999999% of the speed of light, you could travel to the Andromeda galaxy, 2.5 million light years away. In what would feel like just 50 years to you, you could explore the universe in a single human lifetime. But there would be a terrible price. When you returned home, 5 million years would have passed on Earth. Everyone you knew would be dust. The civilization that built your ship would likely be gone. The species itself might have evolved into something unrecognizable. You would be a ghost from the deep past, stepping into a future that had long forgotten you. This is the one-way ticket. This is the kind of time travel we know is physically possible. It isn't magic, it is engineering. We just need enough energy to reach those speeds. But there is a hard limit. You cannot reach the speed of light. As you get closer, your effective mass increases. It takes more and more energy to push you faster. To reach 100% of light speed would require infinite energy. It is an asymptotic wall. You can approach it forever, but never touch it, and at the speed of light itself, time stops completely. Imagine you are a photon, a particle of light. You are born in a star in the Andromeda galaxy. You fly across the void for 2.5 million years and strike the retina of a human astronomer on Earth. To the astronomer, your journey took 2.5 million years, but to you, the photon, the journey took 0 time. The moment of your birth and the moment of your arrival were simultaneous. For light, there is no time. The universe is instant. Light connects every point in space-time directly. This is why we call time a river. It flows. It carries us along. But we have learned that we can build vessels. The International Space Station is a primitive canoe, paddling just fast enough to gain a fraction of a second over a lifetime. Future ships might be speedboats, racing down the current, bypassing centuries in a matter of years. But speed is not the only force that warps the river of time. There is another, heavier, darker, that can seize time and stretch it like taffy. It isn't about how fast you move. It is about where you stand. In 1915, a decade after he dismantled Newton's clock, Albert Einstein unveiled an even grander vision with his theory of general relativity. Special relativity had shown us that speed warps time. General relativity revealed something deeper, that mass itself warps the very fabric of reality. Einstein asked us to imagine the universe not as an empty void with objects hanging in it, but as a fabric, a 4-dimensional sheet called space-time. Place a heavy object on a trampoline, and the surface curves downward around it. Roll a marble across that trampoline, and it won't travel in a straight line. It will follow the curve, spiraling inward toward the heavy mass. To Newton, gravity was an invisible tether connecting planets across empty space. To Einstein, gravity wasn't a force at all. It was geometry. The Earth orbits the Sun not because the Sun is pulling it, but because the Sun is so massive it has carved a valley into space-time, and the Earth rolls along the rim of that valley. As Einstein himself framed it, matter tells space-time how to curve, and space-time tells matter how to move. But here is the crucial insight that goes beyond orbits and planets. Mass doesn't just curve space, it curves time. Imagine the trampoline fabric is made of clocks. In the flat regions, far from the heavy mass, the clocks tick normally. But near the object, where the fabric is stretched tight, the clocks are stretched too. The mechanism slows, the seconds get longer. This is gravitational time dilation. The closer you are to a massive object, the Earth, the Sun, a black hole, the slower time flows for you. Gravity is a break on the river of time, and this is not abstract philosophy. It is measurable right here, in this room right now. Your feet are aging slower than your head because your feet are closer to the center of the earth. Time moves fractionally slower for them than for your brain, which sits 1.5 meters higher. The difference is infinitesimal, measured in femtoseconds, but it is real. Someone who spends their life in a basement apartment ages ever so slightly slower than their neighbor in the penthouse, 50 floors up. The earth holds them just a little tighter, pulling them back in time. In 2010, scientists at the National Institute of Standards and Technology confirmed this by raising one of their atomic clocks just 33 centimeters, roughly a foot above the other. Even over that tiny distance, the higher clock ticked faster. The difference in gravity across the length of a human forearm was enough to desynchronize them. We already saw how this plays out at the scale of GPS satellites, 20,000 kilometers above the surface, where the combination of reduced gravity and orbital speed creates a net drift of 38 microseconds per day, a discrepancy engineers must correct constantly, or the entire navigation system fails within hours, but that is a relatively gentle example. The effect becomes something else entirely when the mass involved is not a planet, but a collapsed star. In the film Interstellar, there is a scene that captures the extreme end of this phenomenon with striking scientific accuracy. The astronauts descend toward Miller's planet, a water world orbiting dangerously close to a supermassive black hole. Before they land, the character Cooper calculates the time cost, 7 years per hour. For every hour spent on the surface, 7 years will pass back on Earth. They land. They spend a handful of frantic hours dealing with a catastrophic tidal wave. When they scramble back to the mothership, which had waited at a safer distance from the black hole, they find their crewmate Romilly. He has aged 23 years. He is gray. He waited alone for decades, while for them, it had been an afternoon. This is not a Hollywood invention. The science developed with Nobel Prize-winning physicist Kip Thorne is accurate. Near a sufficiently massive object, time doesn't just slow, it almost stops. You would look up from the surface and watch the universe accelerating around you. Stars born and extinguished in moments, civilizations flickering like candle flames. You would be living inside a bubble of slow time, while the rest of existence rushed forward at terrifying speed. And this brings us to the ultimate expression of gravitational time dilation, the black hole itself. A black hole is what remains when a massive star exhausts its fuel and collapses under its own gravity, crushed to a single point of infinite density called a singularity. The gravitational field is so extreme that not even light can escape. Surrounding the singularity is a boundary called the event horizon, the point of no return, the edge of the waterfall. As you approach the event horizon, time dilation becomes absolute. To a distant observer watching you fall in, you would appear to slow and then freeze, your image reddening and fading as the light from your body struggles to climb out of the gravity well. You would seem to hang there forever at the threshold, a ghost suspended at the edge of darkness, never quite crossing over. But from your own perspective, you wouldn't stop. You would fall straight through. You would cross the horizon and plunge toward the singularity. Behind you, the entire universe would compress into a shrinking circle of light. What happens to time inside? The equations of general relativity suggest something deeply strange. Beyond the event horizon, space and time exchange roles. Out here, in normal space-time, you are free to move in any spatial direction, left, right, forward, back. But you are compelled to move forward in time. The river carries you. You have no choice. Inside a black hole, that geometry inverts. The singularity is no longer a location in space. It becomes a moment in time. It becomes your future. You cannot avoid it any more than you can avoid next Tuesday. Space itself drags you inward the way time drags you into old age. But is there a way to use this as a passage rather than a terminus? In 1935, Einstein and his colleague Nathan Rosen discovered a mathematical structure hidden within the equations of general relativity. They found that a black hole might not be a dead end. It might be a bridge, a tunnel connecting two separate points in spacetime. This is the Einstein-Rosen bridge. We know it by a more evocative name, a wormhole. If wormholes exist and could be stabilized, they would be shortcuts. Imagine space-time as a sheet of paper. To travel from a point at the top to a point at the bottom, you could draw a line across the entire surface. Or you could fold the paper, bring the 2 points together, and punch through. The hole is the wormhole. Stabilizing one would require what physicists call negative energy, exotic matter with properties that have never been observed. to hold the throat open against the tendency to collapse. But here is where it connects to everything we have already explored. If you could move one mouth of the wormhole at high speed, time dilation would cause it to age slower than the stationary mouth. Bring the moving end back, and you now have a tunnel whose two openings exist at different points in time. Step into one end, and you emerge in the past of the other. A wormhole becomes a time machine. This is mathematically permissible within general relativity. But it creates a problem the universe appears to take very seriously: paradoxes. Stephen Hawking addressed this with what he called the chronology protection conjecture. He argued that the moment you attempt to turn a wormhole into a time machine, a feedback loop of radiation builds up inside it. Vacuum fluctuations entering the future mouth, traveling back through the tunnel, looping again, piling up infinitely until the structure tears itself apart. It is like bringing a microphone too close to a speaker. The screech of feedback destroys the system before anything can pass through. The universe, Hawking believed, actively protects its own history. But gravity has one more trick that goes beyond simple dilation or wormholes. A rotating massive object, the Earth or a spinning black hole, doesn't just curve space-time around it, it drags it. Like a spoon twisting through honey, the rotation pulls the fabric of reality along with it. This is called frame dragging, confirmed experimentally in 2004 by NASA's Gravity Probe B, which detected the subtle twist in space-time caused by the Earth's own rotation. The effect is minor here. Around a rapidly spinning black hole, a Kerr black hole, it becomes violent. Space-time is whipped around at speeds approaching light. A region around such an object, called the ergosphere, is so distorted that standing still becomes physically impossible. You are dragged by the rotation of the universe itself. Some theorists have proposed that a ship navigating the currents of the ergosphere correctly could execute what is known as a closed time-like curve, looping back along its own timeline, returning to a point before it departed. It is one more door in the architecture of time. Whether it is permanently locked remains one of the great open questions in physics. What general relativity ultimately leaves us with is a universe mapped not just by space, but by tempo. The vast empty voids between galaxies, where gravity is almost absent, are the fast lanes time there races ahead. Dense clusters of matter are the slow lanes, and black holes are the stop signs, where time grinds toward a halt. We live on a slow lane. The gravity of the Earth, the Sun, the Milky Way, all of it holds our time back relative to a lone hydrogen atom drifting in intergalactic space. We are aging slower than the void, so returning to Andrew Carlson, his claim of traveling back from 2256 is, from a purely physical standpoint, a question of energy and engineering. Traveling forward is the easier half. Park near a black hole for a few weeks and return to Earth centuries later. The one-way ticket, as we explored before, with traveling back, swimming upstream against the river of time, would require either a stable wormhole, a Kerr black hole's closed time-like curve, or some other structure permitted by the equations but never observed. It would require mastering gravity itself. Perhaps the most quietly unsettling implication of all this is that the past is not truly gone. Because time is a dimension like space, every moment that has occurred still exists somewhere in the block, just as a street you are not currently standing on still exists. The Romans are still building the Colosseum. You are still a child blowing out candles on a birthday cake. We simply cannot reach those coordinates. We are locked into our slice, pushed forward by the relentless increase of entropy. But gravity offers something extraordinary even without a time machine. A window. Because gravity bends light, and light carries information, a massive enough object can act as a lens. We already use distant galaxy clusters as giant natural telescopes. Gravitational lenses that magnify the light of objects behind them allowing us to see the early universe. We look outward and we look backward. Theoretically, if a photon left Earth, curved around a black hole, and returned a boomerang photon, it would carry an image of the Earth from millions of years in the past. We would not be traveling there, but we would be watching. The universe is an archive, endlessly recording, and gravity is one of its replay mechanisms. As you lie in bed, you feel the pull of the Earth. It feels like weight. But now you know it is also time. The gravity pressing you into the mattress is the same force that keeps your clock synchronized with the rest of humanity. The anchor holding you in the now. We have crossed the territory of speed and the territory of gravity. We have seen how both can compress and stretch the seconds. But there is a third path through time, one that requires neither a rocket engine nor a black hole, one that relies on the fragile, ancient machinery of the human body itself. What if, instead of bending time around us, we simply stopped the clock inside us? The universe is vast. Even traveling at 99% of the speed of light, the nearest stars would take years to reach. And we are fragile. We age. We consume resources. We deteriorate psychologically in isolation. The greatest obstacle to interstellar travel isn't the rocket engine. It's the biological clock ticking inside the astronaut's chest. So if we cannot conquer the distance by going faster, perhaps we can conquer it by living slower. This is the concept of suspended animation. In science fiction, it is effortless. Characters climb into sleek glass pods. A cold mist fills the chamber, and they wake a century later, fresh and ready. They have not bent time around them the way a black hole does, and they have not accelerated through it the way a relativistic ship does. They have simply skipped it. The universe moved forward while they waited, motionless in the dark. But can biology actually do this? The answer lies in the relationship between temperature and chemistry. Life is, at its core, a slow fire. It is a continuous series of chemical reactions, collectively called metabolism, that burn fuel to produce energy and heat. Like any chemical reaction, metabolism is governed by temperature. Heat it up, and it accelerates. Cool it down, and it slows. Biologists describe this with something called the Q10 temperature coefficient. For every 10 degrees Celsius you drop the temperature of a biological system, the metabolic rate roughly halves. Cool a body enough, and the fire dims to a flicker. The heart slows. Oxygen demand falls. The cells enter a state of metabolic arrest, not death, but a profound pause. Nature solved this problem long before we thought to ask the question. It is called hibernation. Consider the Arctic ground squirrel. In summer, its heart beats 200 times a minute. It is a creature of high speed and high consumption. But when winter arrives, it retreats underground, curls into a ball, and its body temperature drops from 37 degrees Celsius to -3 below the freezing point of water. Its blood becomes supercooled, remaining liquid the way water can in a cloud, defying the ice. Its heart rate falls to 1 beat per minute. 1 beat per minute. If you dug one up in January, you would be certain it was dead. Cold as stone, rigid, unresponsive. But it is not dead. It is waiting. It remains in this state for up to 8 months, skipping the winter entirely, traveling through time to the spring. Bears do it. Lemurs do it. Certain species of primates do it. But can humans? We are not natural hibernators. Our bodies resist cold aggressively. We shiver to generate heat. If we get too cold, the heart falls into arrhythmia and stops. We are tropical animals, built for the warmth of the African savanna, and our biology fights the cold rather than surrendering to it. And yet, there have been cases that suggest the switch for hibernation might be buried somewhere deep in our genetic architecture, dormant but not deleted. In 2006, A Japanese man named Mitsutaka Uchikoshi went hiking on Mount Roko in October. He slipped, fell into a ravine, and broke his pelvis. Unable to move, he lay on the cold ground as the sun set and the temperature dropped. He lost consciousness. He was found 24 days later. By every medical principle we understand, he should have been dead. A human being cannot survive 24 days without water. But when rescuers reached him, he had a pulse, faint but present. His body temperature was 22 degrees Celsius. He was taken to hospital. He woke up. He had no brain damage. He recovered completely. Doctors concluded that his body had entered a state of accidental hibernation. The cold, combined with the shock and complete immobility, had triggered a metabolic shutdown. His organs had slowed to a near stop, consuming almost nothing, requiring almost no oxygen. He had survived 3 weeks on reserves that should have lasted a few days. In the most literal sense, he had traveled through time, conscious for almost none of the 24 days that passed around him. There was also Jean Hilliard in Minnesota in 1980. Her car slid off an icy road. She tried to walk to a neighbor's house but collapsed in the snow. She was found following morning, frozen solid. Her body was so rigid that her arms couldn't be bent to insert an intravenous line. Her skin was too hard to puncture with a needle. Her temperature was too low to register on a standard thermometer. Her heart was beating 12 times a minute. Her family prayed. The doctors warmed her slowly. And she woke up. No amputation, no brain damage, fully intact. These cases point toward something remarkable. Under extreme conditions, human biology is more flexible than our textbooks suggest. There appears to be a standby mode, ancient and deeply hidden, that the body can access when the alternative is death. NASA is paying close attention. A crewed mission to Mars takes between 6 and 9 months each way. That requires enormous quantities of food, water, and oxygen. It also demands a psychological resilience that is genuinely difficult to sustain. 6 people in a confined metal tube, with nothing outside but vacuum, for the better part of a year. The engineering of the capsule is challenging enough. The engineering of the human mind over that duration may be harder. But what if the crew could sleep through it? NASA has funded research into what are called torpor-inducing transfer habitats. The concept is not full cryogenic freezing. It is something closer to controlled, medically induced hypothermia. The astronauts' core temperatures would be lowered to around 32 to 34 degrees Celsius, just below the threshold where the body begins to shiver, provided sedation keeps that reflex suppressed. At this temperature, metabolism drops significantly. Nutrition would be delivered intravenously. Muscles would be electrically stimulated to prevent atrophy. A robotic system would monitor every vital sign. The crew would sleep through the long middle passage of the journey and wake near Mars, their bodies having spent only a fraction of the energy they would have consumed awake. This is short-term stasis, weeks, perhaps months. But the deeper question, the one that connects to everything we have been exploring, is whether something far longer is possible. This brings us to cryonics. Cryonics is the practice of preserving a human body, or in some cases only the brain, at extremely low temperatures immediately following legal death, in the hope that future medicine will be capable of reversing the damage and restoring life. It is the most extreme wager a person can make. You are betting that death, at least in your case, is not a permanent condition, but an engineering problem that has not yet been solved. The process begins the moment the heart stops. Speed is critical, because brain cells without oxygen begin to deteriorate within minutes. A response team moves in immediately, cooling the body in an ice bath and manually circulating oxygenated blood to the brain. Then comes the critical step. Blood is largely water. and water freezes into sharp crystalline structures that act like microscopic blades, shredding cell membranes from the inside. Simply freezing a human body would reduce the tissue to a destroyed, unrevealable state, so cryonicists replace the blood entirely, flushing it out and substituting a glycerol-based fluid called a cryoprotectant, essentially a medical-grade antifreeze that prevents crystallization. The body is then cooled slowly to negative 196 degrees Celsius, the temperature of liquid nitrogen. At that point, something remarkable happens. The cryoprotectant fluid does not freeze into crystals. It vitrifies. It transitions into a glass-like solid, trapping the biological tissue in a state of perfect suspension. Chemistry stops. Decay stops. Every molecular process halts. A vitrified body could theoretically remain in that state for 1,000,000 years without a single atom changing its position. Currently, hundreds of people and a number of pets are stored in large insulated vessels called douars at facilities such as Alcor in Arizona. To the outside world, they are often called corsicles. To the people who paid for this arrangement, they are patients, waiting for an ambulance that has not been invented yet. Will it work? We genuinely do not know. We have successfully vitrified and revived blood vessels, simple tissues, and even rabbit kidneys. Hamsters have been cooled to near freezing and recovered. But reviving a complete human brain, with its approximately 86 billion neurons and roughly 100 trillion synaptic connections encoding everything that constitutes a person, is a challenge of an entirely different scale. Critics call it an expensive funeral. Proponents say that being dead offers zero chance of survival, and being preserved offers a non-zero one. The arithmetic, they argue, is simple, but step back from the technology for a moment and consider the experience itself. Sleep is already a form of time travel. When you lose consciousness at night, the perception of time vanishes entirely. 8 hours pass in what feels like a single breath. You close your eyes in darkness and open them in light, having crossed the interval without experiencing it. You have, in the most practical sense, traveled to the morning. Stasis would be identical in subjective experience. You close your eyes in one century and open them in another. For you, no time has passed. But the world has moved on without you. The people you knew are gone. The city outside might be unrecognizable. The language may have shifted. You are not a traveler arriving somewhere new. You are a relic, surfacing in a future that did not wait for you. There is a profound loneliness to this. But there is also a profound peace. In nature, the surrender to cold is not weakness. It is strategy. The wood frog of Alaska freezes solid every winter. 65% of the water in its body turns to ice. Its heart stops. Its brain activity flatlines. By every clinical measure, it is dead, a hard, icy mass you could knock against a wall. But come spring, it thaws. The heart restarts. The frog hops away into the grass as if nothing happened, carrying natural antifreeze in its cells that prevented the ice from tearing them apart. Cold in this light is not the enemy of life. It is the preserver of it. Heat is entropy. It accelerates breakdown, drives decay, burns through structure. Cold holds things in place. The Svalbard Global Seed Vault, buried deep in the permafrost of Norway, stores seeds from the world's agricultural crops, a backup of civilization's food supply, kept safe not by any active system, but simply by the cold. Perhaps the distant future of humanity looks something like this. Vast, silent vessels called sleeper ships, crossing the void between stars over tens of thousands of years. No lights, no sound, no air circulating through the corridors. Just rows of vitrified bodies in their pods in the quiet hum of a computer navigating through the dark. On Earth, Generations live and die. Empires rise. Species evolve. But inside the ship, the travelers are suspended in amber, exempt from time, waiting for the signal. This idea touches something deep. We live in an age of relentless acceleration, constant demand, perpetual motion. The fantasy of stasis is, in part, the fantasy of permission to stop, to step off the conveyor belt, to let the world continue without your participation for a while. And in a quieter way, we already practice this every night. As you lie here, let your body begin that ancient process. Feel your breathing slow. Feel the small muscles around your eyes go soft. Your heart rate is dropping. Your core temperature is falling by half a degree, the way it does at the onset of sleep, a ritual the body has performed every night for your entire life, a miniature rehearsal for the long stillness. Imagine you are that Arctic ground squirrel. The burrow is dark and warm. The world outside is frozen and howling. But none of that concerns you now. You have done what needed to be done. You have eaten, you have prepared, and now there is nothing left to do but exist. Your heart, one beat. Then silence. Then another. You don't need to monitor the storm. You don't need to track the hours. The season will change without your help. Spring will come whether you watch for it or not. Your only task is to be here, quietly, waiting. The cryonicists believe that technology will save them. The cosmonauts trust the engineering of their ship. But you have something older than either 4 billion years of biological refinement. You have adenosine building up in your synapses, pulling you under. You have melatonin calibrating your internal clock to the darkness. You have a circadian rhythm as reliable as any atomic clock, honed by 1 billion nights of practice. Your body knows how to do this. It has always been known. The Japanese hiker on the mountain survived because he stopped fighting. He surrendered to the cold, and the cold preserved him. Sometimes the most powerful thing you can do is release your grip on the controls and let the automatic systems take over. Let them take over now. We have looked at speed, we have looked at gravity, we have looked at the cold. 3 different mechanisms, 3 different ways of bending the relationship between a living thing and the march of time. But there is a 4th one that requires no physics, no engineering, no biology at all. Every night, without a rocket or a cryo chamber or a black hole, you look directly into the past. It streams towards you at the speed of light, from distances so vast that the sources may no longer exist. The ceiling above you, if the roof were gone, would be a window into history stretching back nearly 14 billion years. We are going to step outside now, into the dark, and look up. We are trapped in the present. That is the common wisdom. The past is gone, burned to ash in memory, and the future doesn't exist yet. There is only the now, this fleeting sliver of existence that vanishes the moment it arrives. But this is not entirely true. The past is not gone. It is streaming toward us right now at 299,792,458 meters per second. Every time you open your eyes, you are looking into the past. It is an unavoidable consequence of the speed of light. Light is the fastest thing in the universe, but it is not instant. It takes time to travel from one place to another, and that delay, imperceptible across a room, negligible across a city, becomes a chasm when stretched across the cosmos. Look at your hand. The light bouncing off your skin takes a fraction of a nanosecond to reach your eyes. You're seeing it as it was a nanosecond ago. Look at the moon, 384,000 kilometers away. Light takes 1.3 seconds to cross that distance. If the moon vanished this instant, you would not know for over a second. You would still see the silver disk hanging in the sky, serene and whole, a ghost of something already gone. The sun is 150 million kilometers away. Light takes 8 minutes and 20 seconds to make the crossing. If the sun were extinguished right now, we would have 8 minutes of ordinary life, feeling its warmth, watching shadows move across the floor. Before the darkness arrived, we live always in a slightly delayed version of reality, but 8 minutes is nothing compared to what the night sky offers. When you step outside on a clear winter night and find the constellation of Orion, you might notice the bright red star at his shoulder, Betelgeuse. It is a dime supergiant, roughly 640 light-years from Earth. The light reaching your eye tonight left that star around the year 1384. While that single photon was crossing the void, the Black Death had already swept through Europe. Columbus had not yet been born. The Renaissance had come and gone. Empires had risen and collapsed, and every person alive on Earth today had been born. All of that history unfolded while the light was simply traveling. If Betelgeuse exploded 500 years ago, we would not know yet. We would still see it burning, steady and red, on winter evenings. The news is still on its way. The night sky, then, is not a flat ceiling. It is a tunnel, a three-dimensional corridor reaching back through time. The further you look, the further back you see. A telescope does not magnify distance alone. It magnifies time. No instrument embodies this more completely than the James Webb Space Telescope. Launched in late 2021, the Webb Telescope is the most powerful time machine humanity has ever constructed. It was folded like origami inside a rocket, unfolded 1,000,000 miles from Earth, and positioned at a gravitational equilibrium point where it can observe the universe without interference. Its primary mirror is 6.5 meters wide, coated in gold-plated beryllium. But its true capability lies not in its size, but in what it can see. The Hubble telescope, Webb's predecessor, observed primarily invisible light, the same narrow band of the electromagnetic spectrum that human eyes detect. But as light travels across billions of years through an expanding universe, it stretches. The wavelengths grow longer. Visible light shifts into infrared heat radiation. Invisible to us, the most ancient light in the universe has been stretched so far that it can no longer be seen with human eyes or ordinary optics. Webb was built to see exactly this. Its instruments are tuned to infrared wavelengths, allowing it to capture light that has been traveling since the universe was in its infancy, light from the first stars that ignited roughly 200 million years after the Big Bang, 13.5 billion years ago. That light passed through the formation of the first galaxies, the birth of our solar system, the age of the dinosaurs, the rise of every human civilization that has ever existed, and finally, after all of that, it strikes the golden mirror of the James Webb Space Telescope. When astronomers examine Webb's deep field images, they are looking at the universe as it was when it was young. The objects in those images are not distant in the way a mountain is distant. They are distant in time. We are looking at the ancestors of galaxies like our own Milky Way, seeing them as they appeared billions of years before the Earth existed. We are, in the most literal sense, looking at our own origins. Consider what this means for an observer elsewhere in the universe. Imagine a civilization in the Andromeda Galaxy, 2.5 million light-years away, equipped with a telescope powerful enough to resolve detail on the surface of the Earth. If they looked at us right now, they would not see cities. They would not see satellites or roads or the glow of electric light. They would see the light that left Earth 2.5 million years ago. The African savanna, our earliest ancestors chipping the first stone tools, a world of megafauna and open grassland. If they wanted to watch the construction of the pyramids, they would need to wait another 2.5 million years for that light to reach them. The past is not gone. It is expanding outward in a sphere of light, moving away from its source in every direction at once, forever. The image of you in this moment, lying still, breathing slowly, will travel out into space for as long as the universe exists. In 1 billion years, a photon that bounced off your face tonight will be crossing a galaxy that has no name in any human language. We are broadcasting our history to the cosmos whether we intend to or not, but there is a limitation that cannot be overlooked. We can observe the past, but we cannot interact with it. It is read-only. We can watch the light from a supernova that exploded 1,000 years ago, but we cannot warn the star. We are spectators in a cinema whose film was made before we were born, or almost. In 2008, astronomers did something that sounds impossible. They watched a replay. In the 16th century, a star exploded in what is now known as Tycho's supernova. The original light from that explosion had swept past Earth centuries ago, visible to the naked eye before fading. But some of that light had traveled in a different direction, out toward a vast cloud of interstellar dust, where it bounced and was redirected back toward Earth, arriving much later than the direct light. By analyzing this reflected signal, astronomers were able to study the spectrum of an explosion that occurred 400 years ago. They watched a rerun of a stellar death, replayed by the universe itself. This principle, light echoes, is already a working tool of astronomy. The cosmos archives everything. The signal just takes different paths to reach us. This feeds into a deeper realization about the nature of the speed of light. We call it the cosmic speed limit, but it is more precisely the speed of causality, the maximum rate at which any event can influence any other event. When the sun's gravity tugs on the Earth, that influence also propagates at the speed of light. If the sun were to vanish, the Earth would continue orbiting the empty point in space for exactly 8 minutes and 20 seconds before the gravitational signal reached us, and the planet flew off into the dark. We would orbit a ghost. This speed limit creates what physicists call the light cone, the boundary that defines what you can influence and what can influence you. Everything inside your future light cone is reachable. Everything inside your past light cone could have reached you. Everything outside is causally disconnected, unreachable, unseeable, as permanently absent as if it did not exist. And here the universe reveals something quietly devastating. We are losing our view. The universe is expanding, and that expansion is accelerating. Distant galaxies are receding from us faster and faster. There are already galaxies so far away that the space between us and them is growing faster than light can cross it. Their light will never reach us. They are gone from our observable universe forever, not because they were destroyed, but because the space between us stretched beyond the reach of causality. Future astronomers living billions of years from now will look up and see almost nothing. The universe will appear to consist of a single island of stars, our own galaxy, perhaps merged with Andromeda by then, surrounded by absolute darkness. They will have no way of knowing about the Big Bang, no way of detecting the cosmic microwave background, no evidence of the vast web of structure that fills the universe today. They will construct theories of cosmology from an impoverished dataset, and those theories will be wrong. We are living in a privileged moment. The universe is still young enough and small enough in its expansion that we can see its history. Every image the James Webb Telescope captures is a record being made before the archive closes. Now bring this back to the human scale. Your brain is doing something similar every moment you are awake. The light entering your eyes travels to the retina, converts to an electrical signal, travels along the optic nerve, and reaches the visual cortex, a process that takes roughly 13 milliseconds. The signals from your fingertips take even longer. Your brain receives all of these inputs at slightly different times and performs an extraordinary act of editorial fiction. It assembles them into a seamless, unified, apparently simultaneous experience of now, but that now is a construction. By the time you consciously perceive this moment, it is already the past. You are not living in the present. You are living in a continuously updated memory of the last 80 milliseconds. you are always slightly behind. This is why you cannot swat a fly. The fly's nervous system processes sensory information faster than ours. To a fly, your hand descending toward it is moving in something close to slow motion. It perceives time at a higher frame rate. Your 80 millisecond lag is an eternity to it. We each inhabit our own subjective time, not just in the relativistic sense that speed and gravity alter the clock, but in the neurological sense that the architecture of each brain determines how quickly and how finely it slices the incoming stream of the present. The night sky above you holds all of this together. When you look at the constellation Orion, you are simultaneously seeing light that left its various stars at entirely different moments in history. Some decades ago, some centuries, some thousands of years. They appear to occupy the same flat dome overhead, but they are separated by vast corridors of time, their light arriving at your eye in the same moment purely by coincidence of geometry. The night sky is a collage. Roman ruins layered over the Stone Age, layered over the 1990s, all flattened into a single image by the accident of your position in space and time. And somewhere among those stars, someone may be looking back. A civilization 65 million light-years away, in the Virgo cluster, observing Earth with sufficient resolution, would watch the asteroid strike. They would see the end of the Cretaceous unfolding right now. The impact winter, the mass extinction, not knowing that on that same planet, mammals would rise, evolve, build telescopes, and begin looking back toward them. We are connected across unimaginable distance by light, but separated by time so vast it makes the connection more like a message in a bottle than a conversation. We can see the past, we can reach it with our instruments, pull its ancient light into focus, decode its story. But we cannot go there. Not physically. Not yet. The telescope is a time machine that only moves in one direction. Unless, perhaps, there is a back door. The physics of general relativity, as we have already seen, does not absolutely forbid travel to the past. Closed time-like curves, wormholes, the ergosphere of a rotating black hole. The mathematics permits structures that could, in principle, loop back through time, but every time physicists attempt to build a coherent model of such a machine, the universe seems to raise an objection. The energy requirements become impossible. The feedback destroys the mechanism. The paradoxes break the logic. And yet, the question does not go away. We can see the past streaming toward us in every direction. We can calculate where in space the light of any given historical moment currently resides. The light that left Earth during the age of the dinosaurs is now roughly 65 million light-years away, spreading outward in a sphere. If you could get to that shell of light and turn around, if you could somehow intercept those ancient photons, you would see the Cretaceous world live. You would not be changing it. You would not be interacting with it. But you would be watching the deep past of your own planet with your own eyes. The universe has already done the recording. We are just working on the playback. And speaking of playback, your brain is doing it right now. As you drift toward sleep, the day begins to replay. Fragments surface, a conversation, a moment of light through a window, a sound you barely noticed at the time. Your hippocampus is sorting the events of the day into long-term memory, deciding what to keep and what to release. It is your own internal telescope, turning back on the hours just past, archiving them before they fade. The stars above are sending their light to you across millions of years. Your mind is sending its attention back across the hours. Both are forms of the same impulse, the desire to hold on to what has passed, to keep the record, to refuse to let the present become simply nothing. Tomorrow, the light that left your window tonight will be traveling outward through space. It will pass the moon in just over a second. It will pass Mars in a few minutes. In 8 years, it will reach the nearest star. In 100,000 years, it will reach the edge of the Milky Way. and long after everything you have ever known is gone, that light will still be traveling, carrying the faint, scattered information of this night, this room, this moment out into the dark. Nothing is truly lost, it just moves further away. In June of 2009, the physicist Stephen Hawking sat alone in a decorated room at the University of Cambridge. There were balloons, there was champagne on ice, a banner hung on the wall reading, "Welcome time travelers." He waited. An hour passed, then another. The ice melted, the champagne warmed, the balloons began to sag. No one knocked, no one arrived. No one materialized from the future to raise a glass with a man who had spent his life mapping the boundaries of time. Only after the party was over, after the last balloon had been taken down, after the food had been cleared away, did Hawking send out the invitations. This was the elegance of the experiment, if time travel to the past is ever invented. In 100 years, or 10,000, someone, somewhere in that future, should have found the invitation in the historical record. They would have had the precise coordinates, the room, the date, the hour. They should have come. The fact that the room stayed empty was, Hawking argued, the simplest and most honest experimental evidence we have that the door to the past is locked, or, as he allowed with characteristic wit, that time travelers simply have very poor manners. The empty party cuts to the heart of what makes backward time travel so fundamentally different from everything we have explored so far. Traveling to the future, through speed, through gravity, through the long sleep of stasis, is difficult engineering, but it is permitted by the universe without apparent objection. The physics allows it. Nature demonstrates it. We have measured it in atomic clocks on airplanes, in the clocks aboard GPS satellites, in the body of a cosmonaut who came home a fraction of a second younger than he should have been. Traveling to the past is a different matter entirely, and the reason is not a lack of imagination. It is logic. General relativity, as we have seen, contains mathematical structures, closed time-like curves, that trace paths through space-time looping back on themselves. Follow such a path and you would move forward in your own experience of time while arriving at a moment in the universe's past. The wormhole is the most discussed example. A tunnel connecting 2 points in space-time, one mouth held stationary, the other accelerated to high speed and brought back age differently due to time dilation, creating a temporal gap between the two ends. Step into one mouth in 2024 and emerge from the other in 1999. The mathematics does not immediately forbid this, but the moment you try to actually use such a structure, the universe appears to fight back. Hawking described the mechanism in his chronology protection conjecture, which we touched on when discussing wormholes. But it is worth sitting with the full weight of what it implies. As soon as a wormhole is configured as a time machine, radiation, even the quantum vacuum fluctuations that permeate all empty space, begins to loop through it. A photon enters the future mouth, travels back through the tunnel, emerges from the past mouth, and then, because of the time difference, immediately re-enters the future mouth again. It loops. Each pass adds to the energy density inside the wormhole. The feedback builds exponentially, reaching infinite energy in a vanishing fraction of a second, and the structure collapses or explodes before anything as large as a human being could step through. It is identical in principle to holding a microphone in front of the speaker it is connected to. The screech of feedback destroys the system instantly. The universe, Hawking believed, protects its own history with the same ruthless efficiency. But why does the universe care? Why would the laws of physics be arranged to prevent travel to the past specifically, when they permit so much else that seems equally strange? The answer is causality. Causality is the principle that a cause must precede its effect. It is so fundamental to how reality operates that it is almost invisible. We rarely notice it because it is never violated. The egg breaks and cannot unbreak. The bullet leaves the gun before the wound appears. You hear the thunder after you see the lightning. Every event in the universe is downstream of every event that preceded it, and upstream of every event that follows. Causality is the skeleton of time. It is what makes the word because meaningful. Travel to the past puts causality under pressure in a way that travel to the future does not. If you travel forward 100 years, you do not threaten the logic of anything that has already happened. The past remains intact behind you, but if you travel backward, you enter a region of space-time that has already been settled. Events already determined, causes already established, and you introduce a new variable that was not there before. The grandfather paradox is the most famous expression of this problem. You build a time machine. You travel back to 1920. You find your grandfather before he met your grandmother, and you kill him. Your father is therefore never born. You are therefore never born. You therefore never build the time machine. You therefore never travel back. Your grandfather therefore lives. Your father is therefore born. You are therefore born. You therefore build the time machine. You therefore travel back. You therefore kill your grandfather, and so on, without end, without resolution. It is not a puzzle with a clever answer. It is a demonstration that backward time travel, taken seriously, dissolves the logical structure of reality. The universe cannot hold a contradiction. It cannot simultaneously contain a version of events in which you were born and a version in which you were not. Something has to give. Physics offers two serious attempts at resolution. The first is the Novikov self-consistency principle. Developed by the Russian physicist Igor Novikov, it proposes that there is only one timeline and it is, at every point, self-consistent. The past cannot be changed. Not because some force prevents you from trying, but because the past has already incorporated everything you will ever do in it. If you travel back and attempt to kill your grandfather, you will fail. The gun will jam. You will be intercepted. You will lose your nerve. Or, in the version that feels most like a trap, your presence in the past will turn out to have been a necessary cause of the very events you are trying to prevent. You were always there. Your actions were always part of the record. This leads to what is called the bootstrap paradox, or the predestination paradox, a closed causal loop in which effect becomes cause becomes effect with no clear origin. Consider a composer who travels back in time and plays a piece of music to a young musician who learns it, performs it, records it, and eventually that recording is the one the composer heard in the future, which is what inspired them to travel back and play it in the first place. The music exists. But who wrote it? It was never composed. It simply circulates in a loop, its origin erased by the very loop that sustains it. The universe, in this model, is a story that has already been written. You can read it. You can even travel to earlier chapters, but you cannot change the words, because the words you would write are already there, factored into the text. Free will in the past, under Novikov's principle, is an illusion. You are a character discovering the plot, not an author revising it. There is a cold comfort to this. Reality is at least stable and consistent. But most people find it deeply unsatisfying. We do not want to be told that our choices are already made. The second resolution is the many worlds interpretation, which emerged from quantum mechanics and carries with it some of the strangest implications in all of science. Quantum mechanics, at the level of particles smaller than atoms, describes a world of genuine indeterminacy. A particle does not have a definite position or momentum until it is observed. Before measurement, it exists in a superposition of multiple states simultaneously. When a measurement is made and one outcome is observed, what happened to all the other possible outcomes? The Copenhagen interpretation, the dominant framework for most of the 20th century, says they simply ceased to exist. The wave function collapsed to a single reality. The many worlds interpretation, proposed by Hugh Everett in 1957, says something more radical. None of the possibilities disappear. All of them happen. With every quantum event that has multiple possible outcomes, the universe branches. Every branch is equally real. Every branch continues to evolve forward. The result is not a single timeline, but an incomprehensibly vast structure of parallel realities, each one internally consistent, diverging at every moment at every point in space. Applied to time travel, this resolves the grandfather paradox cleanly. When you travel back and kill your grandfather, you do not alter your own past. You branch into a new timeline. Call it Branch B. In Branch B, your grandfather dies. You are never born, and a mysterious stranger appeared from the future and committed an inexplicable murder. In Branch A, your original timeline, your grandfather lived, you were born, and you departed in a time machine, never to return. Both timelines exist. Neither contains a contradiction. You simply can never go home. Time travel in this framework is not travel through time so much as travel between timelines. You are not a visitor to your own past. You are an immigrant to a parallel present that happens to resemble your past. Andrew Carlson, if he existed, did not come from our future. He came from a future, one branch of the countless timelines branching forward from this moment. And when he vanished, he did not return home. He slipped sideways into another branch where the FBI had never heard of him. This is both liberating and melancholy. Liberating because it means causality is preserved. No timeline contains a contradiction. Melancholy because it means that whatever you change in the past, you cannot bring those changes home. You cannot go back and save someone you lost and then return to a present where they are alive. You can only find a branch where they are alive and stay there, exiled from the world you came from. And this brings us back to the party. Hawking's empty room is not just an experiment about physics. It is a statement about the asymmetry of time, the fact that we remember the past but not the future, that we can leave records behind us but not ahead of us. That causes flow in one direction and effects in the other. The invitation was sent after the party. No one came. The arrow of time pointed, as it always does, in one direction only. That arrow has a name in physics. It comes from the second law of thermodynamics, and it governs something called entropy. Entropy is a measure of disorder, of the number of ways a system can be arranged. A tidy room has low entropy. The spam room after a week of neglect has higher entropy. And the second law states something that sounds simple but carries enormous weight. In any closed system, entropy always increases or at best stays the same. It never decreases on its own. Things break. They do not spontaneously reassemble. Coffee cools to room temperature. It does not spontaneously reheat. An egg can become an omelet, but the omelet will never reassemble itself into an egg. Everywhere in the universe, order decays into disorder. Structure breaks down into chaos. Concentrated energy spreads out into diffuse warmth. This is the arrow. It is the only fundamental law of physics that distinguishes the past from the future. Every other equation in physics, gravity, electromagnetism, quantum mechanics, works equally well whether time runs forward or backward. If you film a planet orbiting a star and play the footage in reverse, it still looks like valid physics. But if you film a glass falling off a table and shattering, the reverse, 1,000 fragments leaping off the floor and assembling themselves into a whole glass, is instantly recognizable as wrong. Not because it violates any equation, but because it violates entropy. We remember the past because our brains are entropy-increasing machines. They form memories, which are physical records, which are ordered structures created out of disordered experience. We cannot remember the future because the future has not yet produced the physical traces that memories are made of. Time flows from low entropy to high entropy, from the ordered toward the disordered, and we are carried with it. To travel backward in time would be to reverse entropy, to unshatter the glass, to unmix the coffee, to reconstruct what has been dismantled. It would require not just enormous energy, but a fundamental violation of the direction in which the universe runs. Perhaps this is, in the end, a kind of gift. If the past were accessible, if any moment of history could be revisited and revised, nothing would be permanent. Every loss could be undone, but so could every achievement. Every love could be preserved, but so could every mistake, endlessly corrected, endlessly recorrected by an infinite parade of time tourists with competing agendas. The present would have no foundation. History would be not a record but a battlefield, contested by everyone who ever lived and everyone who ever would live. The fact that the past is sealed is what gives it weight. The fact that you cannot undo what you have done is what makes your choices real. The irreversibility of time is not a prison. It is the condition that makes meaning possible. It is why a promise means something. It is why a loss is worth grieving. It is why a moment of beauty, once past, becomes something you carry rather than something you simply revisit. The party at Cambridge stayed empty. The champagne went flat, but Hawking did not seem disappointed. He seemed, if anything, satisfied, because the empty room confirmed something he had long suspected, that the universe is internally consistent, that the logic of cause and effect holds, that the story of reality moves in one direction and cannot be edited, and there is a quiet peace in that. You cannot go back, you cannot revise today. Whatever happened today happened, and it is now sealed into the block of space-time, permanent, real, beyond reach, but also beyond erasure. The good moments are locked in there too, as fixed and indelible as the difficult ones. Nothing that has ever mattered to you has been lost. It has simply receded down the river, still there in its coordinates, untouchable and permanent. The river moves. It does not stop. In 2003, the world wanted to believe. We wanted to believe that a man could step out of the fog of the future and master the chaos of the present. We wanted to believe that the stock market, with its devastating crashes and irrational surges, was actually solvable, a puzzle that history had already completed. Andrew Carlson was the embodiment of that wish, the trickster who knew the answers. The man who had read the last page before anyone else had opened the book. But like all good myths, his story dissolves when you shine a light on it. The tale of Andrew Carlson was not reported by a serious news organization. It did not emerge from an FBI press conference or a court filing. It appeared in the pages of the Weekly World News, a supermarket tabloid famous for headlines about alien endorsements of presidential candidates, bat-human hybrids, and Elvis discovered alive in a fast food restaurant. It was satire dressed as news, designed to entertain bored shoppers in checkout lines. The story was written as a commentary on the absurdity of financial markets, almost certainly in a single sitting, by someone with a sense of humor and no obligation to the truth. There was no investigation. There was no cell on Rikers Island. There was no bail hearing, no anonymous payment, no vanishing. The man never existed. And yet the story spread. It leapt from the tabloid page to the early internet, was copied and translated and retold until the source was forgotten. It became an urban legend, not because people were gullible, but because it resonated. It touched something real. It gave narrative form to a desire so old and so universal that it barely needs explaining. The desire to know what comes next. The desire to be free of uncertainty. The desire to step outside the flow of time and see the whole river at once, from source to sea. We don't need Andrew Carlson. We never did, because the real story of time travel, the one we have spent this night exploring, is stranger than any tabloid fiction, and it belongs not to a made-up man with a brokerage account, but to all of us. Consider where we have been. We began in an interrogation room in Lower Manhattan, with a question about money that turned into a question about physics. From there we traveled to the chalkboards of a Swiss patent office, where a young clerk imagined riding a beam of light and discovered that time is not a fixed stage, but a river, variable in speed, personal in nature, shaped by the forces acting upon it. We saw how speed stretches the seconds, confirmed not in theory, but in the atomic clocks of two physicists who flew around the world with plane tickets and changed science forever. We watched a cosmonaut return from orbit a fraction of a second younger than he should have been, a small number, but a real one, and a proof. We descended into the gravity well, where mass warps not just space but time itself, where your feet age slower than your head, where a clock raised 33 centimeters runs measurably faster than the one below it, where a planet orbiting close enough to a black hole would age 1 hour for every 7 years that pass elsewhere in the universe. We stood at the edge of the event horizon and looked into the place where space and time exchange roles, where the future becomes a location you fall toward rather than a direction you choose. We lay down in the cold and considered the possibility of pausing the machinery of life entirely, of joining the Arctic ground squirrel in its long stillness, of surrendering to a temperature that holds rather than destroys, of waking on the other side of a century the way you wake on the other side of a night. We visited the patients in their douars, in the Arizona desert, betting everything on a future they cannot see, and we ask whether the question they are posing, can death be an engineering problem rather than a final state, is as absurd as it first sounds. We stepped outside and looked up, and we understood that the night sky is not a backdrop but a depth, a corridor reaching back through time. Every star a message from a different era, the whole dome of the heavens a mosaic of history. We learned that the James Webb Space Telescope is capturing light that has traveled for 13.5 billion years, light that carries the image of the universe's first structures, and that this archive is closing, that the expansion of the universe is carrying distant galaxies beyond our reach forever, and that we are living in a privileged window of cosmic history that will not remain open. We knocked on the locked door of the past. We sat with Hawking in his empty party room, surrounded by unpopped balloons, and we understood why no one came, not because the future is ignorant of us, but because causality is the skeleton of reality, because entropy points in one direction only, because the universe protects its own consistency with the same indifference with which it does everything else. We examined the paradoxes, the proposed solutions, the branching trees of the many worlds interpretation, and the frozen loops of self-consistency, and we arrived at a conclusion that is both humbling and, in a quiet way, freeing. The past is sealed. It cannot be revised, and that is not a tragedy. That is what makes it real. Now come back. Come all the way back, out of the event horizon, out of the cryo chamber, out of the deep field images from the Webb telescope, out of the Cambridge party room. Come back to this room, this bed, this body. You are here. You are now, and the now is stranger than any of the places we have visited tonight. Your brain, at this moment, is performing an act of extraordinary complexity. It is taking electrical signals arriving at slightly different times from your eyes, your ears, your skin, and your inner ear, and it is weaving them into a single, seamless experience of the present moment. That experience is, as we have seen, a construction, a slightly delayed editorial version of reality, assembled about 80 milliseconds after the fact. You are not living in the present. You are living in a continuously refreshed memory of it, surfing the leading edge of your own past. And yet it feels immediate. It feels like now, because the now is all the brain knows how to present to you. It has no other mode. This is the final and perhaps most intimate form of time travel, the fact that consciousness itself is a mechanism for navigating time. Your memory allows you to travel backward, not physically, not to change anything, but to inhabit the past with genuine emotional reality. close your eyes in this moment and you can be in a kitchen from 20 years ago. You can smell something that no longer exists. You can hear a voice that has been silent for years. The neural pattern is real. The experience is real. The past lives inside you, encoded in the arrangement of synaptic connections that make you, you, and your imagination carries you forward. You can simulate tomorrow. You can build a detailed model of the situation that has not yet occurred and use that model to prepare for it, to shape it, to choose a different path through it before it arrives. No other animal does this with the sophistication that we do. The human capacity for mental time travel, for projecting a self backward into memory and forward into anticipation, is one of the defining features of our consciousness. It is the engine of planning, of learning, of hope. We are stranded in the present, yes, but we have windows in both directions, and we are, in a sense, always traveling, carried forward by the current at the same rate as everything else, but uniquely able to look back and forward as we go. Think for a moment about the generations who came before you. The people who survived ice ages with no technology but fire and cooperation, who survived plagues without medicine, who crossed oceans in wooden boats without instruments, who built things that lasted centuries, who loved people who died too young and kept going anyway. Every one of them traveled through time to reach the moment that eventually produced you. You are the destination of an unbroken chain of survival stretching back to the first organism that divided itself in the primordial sea. You are the leading edge of 4 billion years of persistence. You are carrying something ancient forward into the future. Tonight, your only task is to carry it gently. There is a concept in physics, which we have visited several times on this journey, called the block universe. The idea that all moments exist simultaneously in a four-dimensional structure, that the past and the future are as real as the present, that we are simply conscious spotlights moving through a space that is already entirely there. In this view, you are not losing the moments that pass. They are not disappearing. They are being added to the permanent record of what has existed. The day you just lived is now fixed in the architecture of space-time. It cannot be taken from you. It cannot be altered. It is sealed, permanent, real, and the moment approaching, the morning, the light, the world waiting on the other side of sleep, is already there too. Not uncertain, not threatening, already present in the structure of things, waiting patiently for your consciousness to arrive at its coordinates. You don't need to rush toward it. You don't need to worry about whether you will reach it. The river will carry you. It has carried you every night of your life, through every sleep to every morning that followed. It has never failed. It will not fail tonight. Let your breathing slow. Feel the weight of the blanket, the specific temperature of the pillow, the small sounds of the building settling around you. These sensory details are your anchor in the present moment. The data your brain is currently processing, 80 milliseconds behind, assembling into the experience of now. The stock market is closed. The news cycle has paused. The emails are waiting. The demands of tomorrow are still in the future, in their coordinates, not yet arrived. Right now, there is only this, the quiet, the dark, the breath. You have traveled a great distance tonight. We have crossed the territory of Einstein and Newton, of Hawking and Padalka, of the Arctic ground squirrel and the wood frog, of the first stars and the last light. We have looked at time from every angle the science permits, and what we found at the center of all of it, underneath the relativity and the thermodynamics and the quantum paradoxes, is something simple. Time moves. It moves in one direction, and it carries us with it, whether we understand it or not, whether we resist it or not, whether we are awake or asleep. The mystery of time is not something to be solved. It is something to be inhabited. You are inhabiting it now, in this room, in this moment, on this planet, spinning at 1,000 miles an hour, orbiting a star at 67,000 miles an hour. in a galaxy moving through the universe at over 1,000,000 miles an hour. You are on a ship that never stops. You have always been on it. Everyone you have ever loved has been on it with you. And tonight the ship is quiet. The instruments are at rest. The crew is sleeping. Let your eyes go still behind their lids. Let the thoughts that are still moving, still circling, still planning, still replaying the day, let them slow like water finding its level. They will be there in the morning. They will keep. Somewhere in the Andromeda galaxy, the light you are emitting right now is beginning its 2.5 million-year journey. A photon is leaving this room carrying a record of this moment, heading out into the dark. It will outlast everything you have ever built. It will outlast the city outside your window, the language you think in, the civilization that shaped you. Long after the sun has changed beyond recognition, that photon will still be traveling, carrying the faint trace of tonight. You don't need to hold on to this moment. The universe already has it, so let go. Let the seconds pass. Let them pile into minutes, into hours, into the slow architecture of a night well slept. Let the current carry you. The morning is already there, waiting at its coordinates. You will arrive. You always do. Sleep well, and good night.